Hi, Calc students. Let's do some notes on section 5.1, estimating with finite sums. So we'll do a little review first, then we'll get into it. Okay, so let me click this out of there. There we go. So first, quick review. Number one, a train travels at 80 miles an hour for 5 hours. How far does it travel? Well, distance equals rate times time, so my answer would be 400 miles. Right? Not too bad. We can do that. A truck travels an average speed of 48 miles per hour. I see a typo on there. For 3 hours, how far does it travel? 144 miles, or 48 times 3. Number 5, a long distance runner ran a race in 5 hours, averaging 6 miles per hour for the first 3 hours and 5 miles an hour for the last 2 hours. How far did she run? Do a little bit of math. 28. So how do you get that? 6 times 3, which is 18, and then 5 times 2, and that's 10, and then add those two together. Now, which graph would go with each of these problems? So the first one, we're going at 80 miles per hour for 5 hours. So this is your velocity graph, and you're always going 80 miles an hour, okay? So that's that part right here, and then we're going to go for 5 hours, so we stop it right here. So a way to do this is to do a graph with the velocity, and then the area that you have here on a velocity graph would tell you your distance. Okay, same thing with number 2. You went 48 miles per hour for 3 hours. Okay, so 48 would be along here. 3 would come down here. Again, the area underneath that curve is not much of a curve, but the area underneath the curve there would be 144 miles. Then number 5, we've got 2 different ones. 6 miles an hour. Okay, so the y value up here is 6. The x value that we would have right here would be for the first 3 hours. So this area right here would have an area of 18. And then we went 5 miles an hour for the last 2 hours, and 5 times 2 is 10. So the first 2 problems would have a graph that would look like this. The last problem would have a graph that would look like that. It's just a little bit different way of looking at how to do these if you graph the velocity and you want to find the distance. Okay? So at 8 o'clock p.m., the temperature began dropping at a rate of 1 degree Celsius per hour. 12 hours later, it began rising at a rate of 1.5 degrees per hour. For 6 hours, what was the net change in temperature? So 12 hours, and it dropped 1 degree for each of those 12 hours. And then we had 6 hours, and it gained 1.5 degrees, so the net change would be negative 3 degrees, or negative 12 plus 9, which is negative 3. Okay, so we're all talking about rates here. That's what calculus is, the study of rates. Okay, now I won't show you the graph. We'll get into that a little bit later. So what are we going to learn about? Distance as an area under the velocity curve. So that first problems 1, 2, and 5, those first few problems, and then the graphs associated, dealt with that. Accumulation as area under the curve, representing a rate of accumulation. Estimation of area using rectangular approximation. We won't get into estimation of volume using slices, but we will talk about left, right, and midpoint sums. Okay? And this leads to our foundation for understanding integral calculus. Okay? And we'll talk about that a little bit later on what that is. So on your worksheet, here's your graph. So what happens if I have one bar? Okay, so I went for 2 seconds here, and we were up here at 5. So the worst case scenario, or the maximum area, would be a 2 by 5 rectangle with an area of 10 then. And that's with 1 bar, or n being equal to 1. Okay? Or we could do another one. What's the minimum area? So the top one would be this one, and that's an overestimate. An underestimate would be a rectangle down here. It still goes 2 seconds, or x equals from 0 to 2, and we only come up on 1 because that's still the area underneath the curve here. So the minimum area could be 2. Can we get more exact? So the answer is somewhere between 2 and 10. What if we use smaller rectangles? Okay, move my picture out of the way. There we go. If n equals 2, then we would have a rectangle right here from 0 to 1, and then from 1 to 2. And we would call that delta x or delta t, the change in your area or change in your x value right here from 0 to 1 and 1 to 2. If n equals 4, then we go from 0 to 1 half to 1, 1 to 1 and 1 half, and 1 and 1 half to 2. So the width of each of those rectangles would be 0.5. And then you would have to see, okay, how do I want to estimate it? Well, I'm going to go up until I hit my curve and stop. And do it again, and do it again, and do it again. Okay? I believe the actual answer is, we'll talk about that in class when we do it. Okay? Because I'm curious to see what you guys have for answers. So, the book also talks about LRAM, RRAM, and MRAM. Well, what the heck are those? Again, we're going to use the same graph that we had here. LRAM is the left rectangular approximation method. Okay? I used to call it left-hand sum. We also have a right rectangular approximation method, and then a midpoint rectangular approximation method. Okay? So we've got 3 different rectangular approximation methods, left, right, and midpoint. Okay? So what if we had a width of 1? Or delta t equals 1? Well, if we had a LRAM or a left-hand sum, our left-hand side would hit the curve right there, and then we'd go over. Okay, so the LRAM hits it on the left side. Okay, if we change to a right rectangular one, then the right corner hits it. Now, this is obviously going to be an overestimation because we are above it on this part right here, but your right-hand corner hits it, and that's what we call a right rectangular one. Okay, and then we have another one called the midpoint. So what's halfway between 1 and 2? 1.5, so we need to put that into our equation, and that would be our height here. Our width on all of these is still 1, but it just depends on where you want to hit your graph. Now, this one would probably be a little bit over, but not quite because it's a little bit under according to this part here. So again, these are approximations. They're not exact answers. We'll get into that a little bit later, though. Excuse me. Okay, so that was a left-hand rectangular or a left-hand sum. The right-hand sum would be the tall rectangle, and then a midpoint sum would be right in the middle, where the midpoint between 1 and 2 would be. Okay, that's what those 3 things there are talking about. So let's look at a distance problem here. We know the velocity. It's going to be t squared. Okay, where is the particle at t equals 3 seconds? Now, I can't just put 3 in there and say, oh, it's 9, because that's my velocity at 3 seconds. Okay, so what do we need to do? We need to graph our equation, so it's going to be a parabola from 0 to 3, okay? And our delta t is going to be the width of our rectangles. Now, we want to use 12 subintervals. So if you go from 0 to 3, that's 3, and divide it by 12, you'd come up with each one having a delta t, or a width of our rectangles, to be a quarter. Okay, and let's use the midpoint rectangular approximation method. Okay, so it might look something like this. Now, if you were to count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, probably 12, you can't quite tell. Okay, so we do have 12 rectangles that we would have to use to be able to approximate this. If you want to go up to, say we have 24 intervals, it makes it a harder problem, but you get a more exact answer. Okay, so in our interval between 0 and a quarter, what's halfway in between? 1/8. Okay, and remember our equation is y equals t squared, or f of t equals t squared. So what do we do with that? we took our midpoint and we squared it. That's our height. And the area is going to be 1/4 times 1 over 64, and you get 1 over 256. Not the best problem for an example, but it shows you how to do it. Okay? What's halfway between 1/4 and 1/2? That's 3/8. Okay? What's the height of 3/8? So we're going to square that because our function says we're going to square it, and that's our height of our rectangle. That's going to be 9/64, and then we need to take that and times it by 1/4. 9 over 256. Same thing between 1/2 and 3/4. 5/8. Square it, and then we're going to take it times 1/4. Remember, that's the width of our rectangles times the height. Okay, and that's our equation that we have here. Y equals t squared. That gives us 25 over 256. Same thing for these next ones. Now, the unfortunate thing is we're not very far along. We've only done 4 subintervals. There are a total of 12 intervals that we have to go through there. Okay? So we get something that looks like this. Okay? So we did the first one, second one, third one, fourth one. It follows along. We would do the same thing. Now, don't look at the number pattern. There is one, but that just happens to be what it looks like when you go through to do this. Okay? Notice our areas are getting larger. This is a very, very small area. We can't see that real well on our graph. And then we get up here, and it's almost twice as big. It's over twice as big. Okay? We would add all of those rectangular areas up, and that's where you get about 8.98. So that is where we would be. We'd get a distance using our velocity graph, and we're going to use those small rectangles to get that velocity graph. Okay? Let's go on to the next one. So here's a good representation of what a left-hand sum or a left-hand rectangular approximation method is. Here's the middle one with the MRAM or the midpoint rectangles. Okay, notice a little bit above and a little bit below. Okay, so it's a little bit of an overestimate and an underestimate. Do those two equal out? They may or they may not. This one will always be an underestimate. And then if we go to the right-hand side, notice every right-hand side of that rectangle, this is our RAM, or RAM, and every right-hand side is going to be used, and that's going to be definitely an overestimate. Is it always? Well, that depends if your function is increasing or decreasing. We'll talk more about that next time when we go through and do that. Okay? Here's another one. Estimate the area under the graph of y equals x squared sine of x. So this could be kind of ugly looking, from 0 to 3. Okay? Here's what it looks like on our graph. Okay? So when we go through and do this, it says use the RAM program. Okay? So this website here, if you go to it, will give you an approximation using the left-hand sum, midpoint sum, and right-hand sum, or LRAM, MRAD, and RRAM for all those. Okay? They're going to use 50 subintervals, and hopefully our answer is 5.74. Okay? So I'm going to stop right there. Let's go to our website, which is right here. Okay? So x squared plus 1, that's our equation, and we're going to go from 0 to 3. So these sliders, you can move that to be whatever you want there. So if I move it to 2, because that was our... I'm missing it. Okay. But you can start it at any number and end it at any number. 0 to 2 is pretty close to what we had for. And then this one tells you how many rectangles you're going to use. Notice the bigger it is, the more solid it is. Now I'm going to move down here. Here's about 10 bars. We're getting smaller and smaller. We're at 5 bars right there. Okay. Notice if I want to click off the midpoint one, I can click right there. And you can see what they are. So there's my left-hand one. Notice they hit it top left corner every single time. Okay. If I don't want to see that one, I want to see the right-hand one. Then that's going to be an overestimate. Notice the right-hand side of every rectangle is hitting that curve. And if I don't like that one, I want to do the midpoint. There it is right there. Okay? So that's what that website does. So in case you wanted to know, okay, I don't want to do 31 bars. I don't want my n to be 31. I don't want to have to take from 0 to 2, which is 2, divided by 31, and that would give you the width each time. That would be an insanely difficult, long problem. Okay, but let's take a look at that answer or the question we were talking about, x squared sine of x. Okay, I'll click outside of it. There's what our graph looks like. We only want it from 0 to 3. So if I can catch it on there right on 3, wonder if I can move down a little bit rather than trying to be right on it. There we go. So from 0 to 3, well, it looks like my right-hand midpoint is at 31. So let's move that down to about, let's go 3. Okay. Notice my right hand, or midpoint 1 is 6.1. My right hand is 5.75. My left hand is 4.48. If you want to see what they look like separately, you can click off those boxes and take a look right there. So what happens if I want n to be bigger? I want it to be 5. Okay. There are my two numbers there. The higher you go, the more accurate it's going to be. I don't know how far I can go until it starts. It looks like it's going to be about a 5.8 maybe. Notice I'm going up like 33, 35, 40. I think it goes up to 50. So what's the area underneath that curve? Well, the best one is going to be about 5.78. Now, if I click those off, you still can't see that very well, and unfortunately, I don't think I can zoom in on it. But you get a general idea of what the midpoint rectangular approximation is, the right hand or right rectangle approximation, or the left one. Okay, when we go through and do this. Okay, so you've got a worksheet to do, and book problems. There's only 2 problems on the worksheet. There are some in the book that you have to do. Some of them ask you to do n up to like 100 and 150 or 1,000. This program only goes up to 50. So I've narrowed down some of your homework problems, only those that ask for less than 50 or the number of bars being less than 50. Okay, good luck on your homework. If you have any questions, you can always get a hold of me during SRB or any other time. Thank you.